Yeah, so thank you for coming. So today I'll talk about the unsupervised alignment of Qualia structures, which are now mentioned a little bit. And also, as a subtitle, I'll also consider the direct communication experiences, which actually I discussed with Julio a little bit in the summer school. So these are the people I collaborated with, and Genji and Ken in my lab, and Ariel and now in Nao's lab, and Julio about the discussion, about direct communication experiences. So let me first, start with this question: how can we, directly transfer one person's experience to another person's experience? Like, this problem is, of course, very, very challenging. And at this point, we are very far from, practically solving this problem. But I want to consider this problem as a theoretical exercise, which hopefully helps you to understand the, importance of our approach and also IIT. Then, let's assume that you have access to every neuron in person A and also in person B. And then you can stimulate these neurons as you wish. Then how should you stimulate person B's neurons if you want to just directly convey person A's experience to person B's experience? So what is necessary for this program? So first, how can we compare subjective experiences, Qualia, between different individuals? And second, how can we connect Qualia and the neural activity? So our answers at this point is that the first problem should be addressed through structural comparison and unsupervised alignment. And the second problem should be addressed by examining the cause-effect structure proposed by integrated information theory IIT. So here is the outline of today's talk. I just proposed this theoretical exercise, direct communication of experiences, and there I introduced structural comparison and unsupervised alignment. And then I'll just show you an example of a structural comparison. And then I'll move on to how do you connect neural activity structures between different individuals. And then lastly, I'll little bit talk about the cause-effect structures. Okay, then first part is that structural comparison of Qualia structures. So this problem, the motivation comes from this ancient philosophical problem. Like, do different people experience the same redness of red? So we can think of that maybe that person B's experience is something completely different, like blue. So this is a famous, embodied Qualia sort of experiment. And people think that, there is no way to, directly compare Qualia between different people. But, as I, now mentioned that we are taking a structural approach. So we can at least quantify the relationship between a quail and other Qualia, like how similar red and orange, and how similar red and green, and so on. And then we can make structure of similarity relations, which we call Qualia structure of colors. And then by quantifying this relationship between quail and other Qualia, we can at least compare Qualia on a structural level between different individuals. That's our basic approach. And then what we need for this structural approach to assess, this ancient philosophical question, like, is my red same as your red? So we have a Qualia structure of person A and a Qualia structure of person B. And we need a measure for quantifying the similarity or distance between Qualia structures of person A and B. And also, we want to have a mapping between Qualia structures that identifies which Qualia in one person corresponds to which Qualia in another person, like red corresponds to which color in a different person. So to do that, usual method is called representative similarity analysis or supervised alignment. In this framework, we assume that red should correspond to red, and purple should correspond to red, and blue and corresponds to red. We assume this implicitly in this supervised alignment. So we use the label of external color stimuli. But and then we compare how similar these shapes, the structures are, given these assumed correspondence between Qualia structures. But we cannot assume that same stimuli evoke the same conscious experiences Qualia between different persons. Actually, this is the very question we are going to address, like whether my red the same as your red. So we do not want to assume this correspondence beforehand. So rather, what we want to do is that we want to explore all possible correspondences, like this my red could be this, or this, or this, or maybe you are around here, or something like this. So by exploring all possible, correspondences, what we want to do is that to find the, closest alignment between structure. So to do this, we do not use color labels of external stimuli. So we do this just like a blind. So we need to compare Qualia structures without assuming correspondence. That's our strategy, and this is called unsupervised alignment. And then to solve this unsupervised alignment, this is much more difficult than the supervised alignment. So we need a mathematical trick to perform this unsupervised alignment. And we find that actually this optimal transport method is one possible effective method to do this unsupervised alignment. So I'm not going to explain the details, but I'm going to use Gromov-Wasserstein optimal transport. And the Gromov-Wasserstein optimal transport is an unsupervised alignment method that aims to find the alignment between two structures based solely on the internal relationship, like only the dissimilarity between within the same structure, within the structure A or within the structure B. So we do not use our relation across different people, okay? We only use the internal relation within the same person. Then, again, important thing is that the correspondences between points, by the way, points represent colors in our case. So correspondence between points are not given in advance. Instead, they are determined during this alignment procedure. So yeah, just ignoring the mathematical details, but what we need to do is that, try to minimize this quantity and, find the optimal transportation plan, which is the optimal sort of mapping between two structures, like which color should correspond to which color in the other structure, something like this. And then, I'll show you the particular example of a structure comparison, which is a similarity structure of 93 colors. As now a little bit mentioned in his talk, we actually performed the similarity judgment experiments of 93 colors via large-scale online crowdsourcing. So we collected color neurotypical participants data from 456 participants, and color atypical participants are 257. Then we obtained this kind of dissimilarity matrix of color neurotypical and the color atypical participants. And then we performed the following alignment. First, we perform whether the structures are aligned between non-overlapping color neurotypical participants group. And also, we will assess that whether the color structures are aligned between color neurotypical and the atypical participants. So let's look at the first investment. First thing. So we first divided that participants into non-overlapping groups consisting of roughly 100 participants. Actually, each participant only gives us 200 reports of similarity judgments. So by filling in all of the dissimilarity in this 93 by 93 matrix, we aggregated the similarity responses from many participants. And then we get the sort of averaged response from color neurotypical participants group 1 and the color neurotypical participants group 2. And then based on these dissimilarity matrices, we did this Gromov-Wasserstein optimal transport. And then we obtained this optimal mapping, optimal transportation plan. And this diagonal line actually means that, most colors in one group correspond to the same colors in the other group with high probability. So the important issue is that we did not use external labels at all. We did this, alignment, mapping, without looking at external labels. But we can find that these colors actually map, meaning that these colors relations are similar between different participant groups. Okay, then, this is the, visualization or movie. We did the same, similar unsupervised alignment across, 5 groups, 5 non-overlapping groups. So there are actually the points from different non-overlapping 5 participant groups. And we can just perform this kind of alignment without looking at color labels. Okay, these color labels are used only for just visualization. Okay. Yeah, so far so good. So this, this, result is sort of expected. We, just use the same color neurotypical participant groups. So this is just, proof of concept of our methodology. Then let's move on to the non-trivial case, alignment between color typical and the color neurotypical participants. Yeah. So we have, dissimilarity matrix for color neurotypical and the color atypical participants. And actually, the simple correlation between these dissimilarity matrices is reasonably high, 0.6. So they are similar, reasonably similar. But it turns out that these we cannot find the good alignment between these two structures, meaning that most colors do not correspond to the same colors. So we cannot see the diagonal lines as we saw in the color neurotypical alignment. So the reason why we cannot align between these different participant groups is that obviously this structure difference. Our color atypical participants is actually red-green color blind participants. So as a visualization, so these are the sort of MDS from color atypical participants. So greenish colors and the reddish colors are close to each other, while the greenish colors and red colors are far in color neurotypical participants. So this structure difference is, of course, likely to prevent the unsupervised alignment between the embeddings of color neurotypical and the atypical participants. Yeah, but you will think that this is sort of natural because, of course, that we already really well know that these people are really different in terms of color perception. But the interesting question is that this: are these structures are completely different, or are they partially equivalent? So I tried to assess this question and found that actually yes, the next, like there seems like a partially matching structure even between color neurotypical and atypical participants. That's what we found. So how did we find this? Like we simply excluded greenish colors, like 12 greenish colors from the 93 colors, and then we did the same, unsupervised alignment. Actually, in that case, we found a very good alignment between atypical and the typical participants. So we can see the nice, diagonal line, which means that same color corresponds to the same colors. But this does not happen when we exclude only reddish colors. We cannot see the good alignment in this case. So as a control, we did the same thing for yellow and blue colors, but we found that only when greenish colors are excluded, the colors similarity structures can be aligned in unsupervised manner. So this indicates that partial color structures without green colors are striking similar, so similar enough to be aligned between color typical and the atypical participants. That's, I think, the very non-trivial finding. So this finding is consistent with the previous study by Shepard and Hooper. This study investigated the similarity structure of only 9 colors. So this is sort of like a schematic and a smaller version of our experiment. But what they found is that this kind of structure for 9 colors, for color typical and red-green color atypical participants. So let's look at this structure. This is sort of like a smaller version and really schematical, but yeah, just a model. Let's consider this. And then, as you can see, in the color typical participants, red-green are far away, but green and red are close in color atypical participants. But what about the rest of colors? Actually, if we exclude green colors, this and that, then we can see the relationships are sort of preserved, right, between the color typical and the color atypical participants. I think that that's what we observed even in 93 colors data, our 93 colors data. On the other hand, like you can see the very similar structures without green color. But if we exclude red colors, we can see a difference in like greens are relationally different between 2 participants groups. Okay. So that's, I think, that what we found are even in these 93 color similarity structures. And then our finding of partially matching color structures without greenish colors raises several questions. Like, how does green stimulus feel to color atypical individual? Is it like a red or something else? And also, maybe there is some missing color around here, like that should correspond to green. But are there any stimuli for color atypical individual that correspond to the experience of green for color atypical individual? That kind of question so far, has not been addressed, but we are very interested in, and we'll address this question by using the psychophysics experiments and also this unsupervised alignment technique. Okay, so yeah, let's get back to the original question. Like, how can we transfer one's experience to another person's experience? So the remaining issue is that, of course, how can we connect Qualia and the neural activity? But before going that, let's consider just a problem of transferring neural activity in person A to that in person B. So I would argue that to transfer one's experience to another person's experience, we should similarly also consider the structure mapping between neural activities. This is actually not structure mapping, but the usual method of connecting neural activity via external stimuli. So usual method is that we just record the neural activity given by some bunch of external stimuli, like a red, orange, blue, whatever. And then we also have the same responses to the same stimulus set in person B. And then we have a bunch of our neural responses. And then we do some mapping between XS in person A and Y is a neural activity in person B, YS. And then we now have some mapping between X and Y. But, so let's assume that we establish this mapping. But if we induce the activity of FXS to another person's neurons, can we say that these people have the same experience? Yeah, this is actually no. Again, as I argued, it is not guaranteed that same stimulus evokes the same or similar experiences between different people. So this ensures that inducing the corresponding activity for same stimulus, but this does not guarantee to induce same experience, right? So we need to do the structure mapping. Like for example, what if the neural activity to different stimuli look like this? Like in person A's experiences something like this. Person A's neural activity. So this is our dimension of some neural activities. And then we map the relations between neural activity in this space in person A, and we get the same relations are in person B, but these relations are really different. Like in person B, red and green's neural activity are close. So in this, this is like a red-green likely situation for red-green color blind participants. But in this case, the green stimulus is not likely to evoke the same experiences, right, between person A and B. So again, we need to assess that whether two structures match without looking at external stimuli. So external stimuli basically do not help to connect the experiences across individuals. So we do this kind of unsupervised alignment even for a neural activity level. Okay. So in this case, this and that shape are closely matched. But this case, these structures do not match. So in this situation, it's probably really difficult to induce similar experiences across different people. But let's consider this case, the case where we can have structure matching between different people. So in this case, so assume that after unsupervised alignment, the same external stimuli match. Very clean situation. So in this case, the red stimulus or corresponding neural activity in person B evoke a similar experience of red as person A, right? So that's very easiest case. But I expect that different situation happens. Like, after unsupervised alignment, the two structure exactly match, but the neural activity evoked by the red stimulus in person A actually corresponds to that evoked by the green stimulus in person B, meaning that the green and red neural activity are sort of swapped in comparison with person A. So in this case, if we want to transfer the experience of red for person A to person B, we should use the stimulus of green, not red, right? Or induce the corresponding neural activity in person A neurons. That's what we expect from this kind of structural mapping approach. But the important question is this: is structural equivalence sufficient? Like, assume that two structure of neural activity turn to be equivalent or isomorphic between different individuals. Do they have a similar experience? Yeah, no. So this is an extreme example. So let's consider the system A, which has a really complex connections among the units in the system. And the system B, there is no internal connections between the units. And we can see the bunch of neural activity and assume that at the structural level, these activities exactly match between X and Y. But even if the structures of neural activity match, can the system B ever have similar experience as the system A? Yeah, I think that everybody agrees that no, right? Seems like a no. And also another example is that which now mentioned, we actually found that we can, find a very good alignment between human color neurotypical participants and GPT-4 deep neural network models for the these are 93 color similarity structures. Does this mean that GPT-4 has a same or similar subjective experience of colors with humans? Again, no. So what is missing? Structural equivalence of neural activity is not sufficient. So we need some theory to address this question in some unified manner. IIT is one of or maybe the only so far the only possible are candidates of that theory, that kind of theory. So IIT posits that subjective experiences are determined not only by neural activity, but also by the intrinsic causal relations between units, these connections within the system. So if we have exactly same systems in terms of internal causal relations, then inducing the structurally equivalent neural activity to Y, we are sure that the two systems will have the same experiences. That's what our IIT expects. Okay. So finally, I'll just briefly mention the cause-effect structures. So that the easiest example is probably fine. Like if we have exactly the same system, then if we induce the same neural activity, then we get the same experiment. That's fine. But of course, the actual situations are not like this. We have a more or less similar causal relations between neurons. And then can we say that whether we have similar experiences? That's what we want to address, right? So for this, we need some theory to quantify the so-called cause-effect structure. So IIT posits that cause-effect structure determined by neural activity at a given moment and the causal relations between units is identical to the subject experiences. So what is cause-effect structure? Just in short, Julia will talk about that in detail. So I just make the explanation short. But the cause-effect structure is like given neural activity at some moment, then what is the likely cause of this neural activity, and what is likely effect given this neural activity? So at the past and at the future. And so leaving aside the mathematical details, so this is also a structure. It's a complicated structure. So we call it, cause-effect structure. And this, cause-effect structure is identical to consciousness. That's, what IIT proposes. So IIT predicts that the neural activity alone is not directly related to subjective experiences. Thus, the proximity of neural activities may not directly reflect the similarity of subjective experiences. So if we, have experimental support for this prediction, I think it's going to be a very important supportive evidence for IIT, but we have not yet so far got such evidence. But anyway, so the important thing is that again, that this extreme case. So if we have some complex connections inside the system, then we have a cause-effect structure for a particular neural activity. And then what we should consider is that complicated thing, structure of cause-effect structures. Like this point, in this case, represents not just neural activity, but cause-effect structure given by this neural activity. And also cause-effect structure given by neural activity, blah, blah, blah. And then, distance between cause-effect structures correspond to our experiences, dissimilarity of two experiences. That's a prediction. And so again, important thing is that the distance between neural activities does not necessarily reflect the distance between the cause-effect structures. For example, that in terms of neural activity, X1 similar, but in terms of cause-effect structures, this and that can be really different. Something like this theoretically happens. And also in this, very boring system, like with no connections, we expect that we do not have anything, like no structure is formed. Every neural activity is the same in terms of cause-effect structure because there is no causal effect, anything. So meaning that every neural activity has a, basically zero distance between them. Okay, so I'll wrap up. So this is the, actually that, recent advancement from IIT. So IIT now actually argues further that, by examining the cause-effect structure itself, we would be able to determine that it should correspond to a particular phenomenology of Qualia, like space, time, visual, auditory, etc. So there is actually, really much progress after, IIT3, which I did 10 years ago. And then, by listening to, this is one slide from Julio's talk, and by listening to Julio's talk, I think that I hope that you will be able to get the sense what kind of meaning we can extract by examining cause-effect relations. IIT has made really a lot of progress in this aspect, like meaning of cause-effect structures, and which I was really impressed in the, actually summer school last week. Yes. So just wrap up, this is a summary of my talk. So the question is, how can we directly transfer one person's experience to another person's experience? I argue that structural mapping and unsupervised alignment is essential. And also, considering cause effect structure is essential to connect neural activity and qualia. So from neural activity, we should get the cause effect structure, and also we should get the structure of cause effect structures. And then do the unsupervised alignment. I think that theoretically we can transfer one person's experience to another person's experience. That's our claim. Yes, that's it. Thank you for listening.
Maybe we can take some questions, and we also will take 5-minute break after this.
I have a question about the transfer. So here you assume all the transfer occurs between structure with the same number of nodes or elements, but they don't have the same number of nodes.
Of course, that it's possible. Like we can have different number of nodes. Just for the sake of explanation, I show the same number of nodes, but this unsupervised alignment works even for the case of different number of points.
So assuming, let's say the one on the left hand is 10 nodes, the one on the right is 2 nodes.
Yes.
So after transfer, what will happen?
We can see that this point should correspond to the 2 points. Then this point, I mean, we do not consider the one-to-one mapping between nodes. Rather, one-to-many mappings between nodes, or like as I showed that we allow that not strict one-to-one mapping, but rather we sorry that maybe this. So we can have mapping like around here. So in that sense that we can have a different number of points, and then we just transfer.
Okay, so it will indicate, for example, if let's say 5 nodes on the left
hand
to the same node on the right hand, then it means the person on the left hand might have 5 different spheres.
Exactly.
The person on the right hand.
Yes.
Oh, okay.
Yeah.
Thank you.
Thanks for the talk. I don't know this field really. I don't understand why if even if you have the same structure, you should necessarily have the same perception of the color.
No.
I mean, they're not just rotated or something.
Yeah. It is not, guaranteed actually. But what we can, assess is just, whether the two people's experiences are relationally same or not. But whether the one person has a really exactly same experience, that type of question cannot be assessed with this approach. But at least we can say that these people have similar relationally similar experiences.
Thank
yes.
You. Actually, in the last part, you have these neural activities.
Yeah.
Why are you talking about neural activities and not, for example, something like subcellular genetics or something like that? Or, where have you got this level from?
That's another important question. Like, how can we know that which neural activity corresponds to?
Not just neural activity, but other stuff goes on.
That's another important question. Like, which factors in the brain actually contributes to consciousness?
Right.
Yeah, that type of question is also needs to be addressed. But for now, I just assume that neurons are some direct correlate to conscious experiences. But this type of question actually also can be addressed by IIT. Yep.
Thank you.
Yep. Thank you.